If you recall from section 2, when we initially talked about limits, we said the value of a limit had to be some number L, which was finite. And in this video, we're going to be taking a look at something a little bit different way of thinking about limits. So we're going to be looking at infinite limits. Now, obviously, infinity is not a finite value. So technically, in these situations, the limits aren't going to exist. But the value of infinity or negative infinity is used to describe the unboundedness of our curve as it is getting closer and closer to some x value. So infinite limits happen when we have vertical asymptotes, and generally those come from rational functions. So if we have a rational function, a vertical asymptote happens when the denominator is 0, right? So the value that makes our denominator 0 is 2. So that's what we have here. We don't know the value at 2 because it's not defined there. So we're going to take a look at some numbers really close to 2 on either side and see what happens to our function. If you think back to pre-calculus and you think about vertical asymptotes, if your graph is approaching a vertical asymptote, we know that it either has to go up or it's going to have to go down, something like this, right, off to either positive or negative infinity. And the hard part is figuring out which way it goes. So how do we do that? Well, let's take a look. So if I pick a number to the right of 2, like 2.5, and I plug it in, I'm going to end up with 6. And as I get closer and closer and closer to 2, what's happening to my y values? So at 2.1, I have 30. 2.01, I have 300. If I'm 1,000th away from 2, I get 3,000. And these numbers are just getting larger and larger and larger and going off toward positive infinity. Off toward positive infinity, right? So if I were to pick 2.0001, so 1/10,000th away from 2, we'd probably get 30,000 and so on. So we can see that as our number is getting closer and closer to 2 from the right, our number is going off to positive infinity. Now, why is that? So if you think about this, right, in any fraction, as the denominator gets smaller, if the numerator is unchanging and the denominator is getting smaller, then that means that our overall fraction is getting larger, right? If I was dividing 5 things amongst a smaller and smaller and smaller amount of people, right? Let's say I had 5 items and I was dividing it amongst a smaller and smaller amount of people, each person would get more of that thing. So this idea works in this situation too. So if I look at numbers to the left of 2, what happens? So if I started at 1.5, 1.5 plugging in gives me a negative 6. Plug in 1.9, I get negative 30, and then negative 300, negative 3,000. So as I'm getting closer to 2 from the left, these numbers are getting more and more negative. Because if I plug in 1.999, that number on my denominator is a very, very small negative number, and then a positive divided by negative is going to be negative. So this is going to go off toward negative infinity. So this is telling us that our left-hand limit, as we approach 2 from the left, we are going off toward negative infinity. And as I approach 2 from the right, I'm going off toward positive infinity. Now, technically, again, these limits don't exist, but these are describing the unboundedness of our function at 2. So when we talked about vertical asymptotes in pre-calculus or in algebra 2, we basically just said it's a vertical line that our graph cannot cross, right? And it happens from domain restrictions. So let's give a little bit more formal definition and using calculus. So we say if our function's value is approaching infinity or negative infinity, as our x value is getting closer to some value of c from either the right or the left, then we can say that the vertical line x equals c represents a vertical asymptote. So essentially all this is saying is if as you approach some x value from either the left or the right, it blows up to infinity or goes down to negative infinity, then that means that the line that it's approaching, the number it's approaching, represents a vertical asymptote. So the way that we find vertical asymptotes is still going to be similar to what we did in pre-calculus, right? We're still going to look at what makes my denominator 0, but to verify that it's in fact a vertical asymptote, we have to look at the limits from either side and see if they go off to infinity. So whenever we're dealing with rational functions, we often do interval testing. We test intervals. We test the numbers that make it 0. So we look for intercepts, and then we look for domain restrictions like asymptotes. So in this situation, I care more about the intercepts. And so I think I'm going to have sorry, not the intercepts, about the asymptotes, what makes my denominator 0. So I think I'm going to have a vertical asymptote here at x equals 2, right? Because that makes my denominator 0. So to verify that it does in fact make a vertical asymptote, I have to look at my limits from the left and the right. So if I plug in 2, right? So if I'm just looking at 2, I don't actually know its value there because its value is not defined. But if I pick a number just a little bit to the right of it, let's say 2.1, what would my right-hand limit be? So this is the limit as x approaches 2 from the right of f of x. So if I plug in 2.1, my top is going to be positive. It would be 8.4. If I plug in 2.1 in the bottom, it's going to be 0.1. It's also going to be positive. So we're going to have a positive number divided by a positive number. And as my numbers are getting closer and closer to 2, if I put like 2.01, then my denominator is going to be getting smaller and smaller and smaller, meaning my overall fraction is going to be getting larger and larger and larger and going off to positive infinity. So that means that that limit from the right side is positive infinity. What's my limit as x approaches 2 from the left? So if I pick some number to the left of 2, like let's say 1.9, and I plug that in the top it's positive, right? In the bottom though, 1.9 minus 2 is negative 0.1. And so now I have a positive number divided by a negative number. So as I pick numbers that are, again, getting closer and closer to 2, my denominator is getting smaller and smaller and smaller. And it's basically getting to be smaller and smaller negative numbers. And so this whole quotient is going to be getting bigger in the negative direction. So it's going to be going off to negative infinity here. If you have a problem like this, where you have a big kind of complex rational function, the first thing that we should do is try to simplify. So I'm going to simplify by factoring. So if I factor the numerator, I'm going to get x squared, oh, whoops, sorry, not just x squared, x plus 3 times x minus 2. And then in the denominator, the leading terms are going to be 2x and an x. I think I'm going to have a 7 here and a 2. And this one should be positive and negative. 2x squared minus 4x plus 7x, so that gives me 3 minus 14. Yeah. Okay, so in doing this, we see that we end up with this common factor of x minus 2 that cancel. And this canceling actually doesn't impact the limit, because if you think about the value of a limit, when we have factors that cancel, those factors actually turn out to be a hole in our graph, right? And if you think about the limit around a hole, basically, if you have your function that's approaching the same point from both sides, if you just remove that actual value of the point, it doesn't impact the limit itself. So removing this is not actually going to impact our overall limit. So let's find the limit of h of x. Well, actually, first we need to look at vertical asymptotes. So the vertical asymptotes are going to happen at what makes our new reduced rational function 0. So that's when x equals negative 7 over 2. Which would be negative 3.5. For ease, we'll probably use this decimal here. And then we know that we have a hole when x is positive 2. Okay, so let's take a look at the limits around negative 3.5. So the limit as x approaches negative 3.5 from the right of h of x is going to be the same as the limit as x approaches negative 3.5 from the right of our reduced function, so x plus 3 over 2x plus 7. And we'll figure out what that is here in just a second. And I'm going to be a little bit lazy, and I'm actually just going to copy all of this stuff to help me rewrite my limits. Well, let me first move this down here. And then copy this. So there we go. And I'll just make it from the left. So make it from the left here like this. Perfect. And then we'll evaluate these limits. So if I'm looking at negative 3.5, sorry. So negative 3.5 here in the middle. I don't know its value because its value is undefined. But if I were to pick a number a little bit to the right of it, say negative 3.4, and I were to pick a value to the left of it a little bit, negative 3.6, what would happen? So if I plug in negative 3.4, so I'm approaching negative 3.5 from the right, if I plug that in, what do I get? So in my numerator, I'm going to get a negative number. Negative 3.4 plus 3 is something negative. Negative 3.4 times 2, that's going to be negative 6.8. Negative 6.8 plus 7 is something positive. So as I'm getting closer and closer to negative 3.5, this is going to be getting more and more negative. So this is going to be going off to negative infinity. If I pick a number from the left of 3.5, like negative 3.6, my numerator is going to be negative. Negative 3.6 times 2, that's negative 7.2. So that's going to be a negative because negative 7.2 plus 7 is negative 0.2. And now I have a negative divided by negative, which means that would be positive and go off to positive infinity. So I could pick numbers a little closer to negative 3.5, but they're all going to trend that same way, where the top will be negative and the bottom will be negative. And so those would be our limits there, which does in fact confirm that we have this vertical asymptote here at negative 7/2. Okay, so in this example, we have the same function, x over x plus 2 quantity squared. The only difference is this one we're approaching from the left, and this one we're approaching from the right. So let's go ahead and take a look at these limits. So again, I could consider where our function is 0, right? What makes our function 0? But that's not really going to impact my infinite limits or my limits around negative 2. So I only care about what's happening around negative 2 because that's what makes my denominator equal to 0. So what is the limit as x approaches negative 2 from the left? So again, here at negative 2, so let me write that limit. The limit as x is approaching negative 2 from the left of x over the quantity x plus 2 squared. Okay, so negative 2 is right here. So as I'm approaching from the left, like negative 2.1, what happens? When I plug negative 2.1 into the numerator, it's going to be negative. When I plug negative 2.1 into the denominator, I get negative 0.1, but that's being squared, so it's going to be positive. And again, as I get closer and closer and closer to negative 2, my numerator is always going to be negative, and my denominator is always going to be positive because we square it, so it'll be positive. So the whole thing is going to have this behavior, which means it's going to be ultimately a negative number, and it's going to be getting closer and closer to negative infinity. Now, if you think about pre-calc and what we learned in pre-calculus about rational functions, we know that there's this idea of multiplicity. And multiplicity arises not only in zeros, but also in asymptotes. And if you have a multiplicity in a rational function in your denominator that is even, so you have an even multiplicity on an asymptote, essentially what that tells me is that from both sides, my graph goes in the same direction. If this was something that was odd, like if it was 3, then that means they would go in opposite directions. So one would go down, one would go up. So with an even multiplicity in my asymptote, this tells me that this is also going to go down. And if you wanted to confirm, you could pick a number to the right, like negative 1.9. Again, plugging into the numerator would be negative. Plugging into the denominator would be positive, giving us a negative infinity. So this limit would be also negative infinity, the same as this one. So there are a few properties of limits, and these ones are properties that involve an infinity. So if we let c and L be real numbers, and f and g be functions such that the limit as x approaches c of f of x is infinity, and the limit as x approaches c of g of x is L, so f has an infinite limit and g has a finite limit, these properties hold. So the sum and difference property, basically if you add a finite limit to an infinite limit, your limit's infinity, right? So if you add some small number to something infinite or subtract some small number from something infinite, it's still going to be infinity. Product, if you multiply an infinite limit with a constant or with a finite number, that's going to go off to infinity as long as L is greater than 0. If L is less than 0, if your limit is something negative, then it's going to go off to negative infinity. If you have a finite number divided by infinity, right, then that would be 0. And that kind of makes sense because if you have, let's say, 5 in your numerator and you start dividing by numbers that are bigger and bigger and bigger in your denominator, then that means that that number overall is going to be getting smaller and smaller and smaller. 5 divided by 10 million is a very, very small number compared to like 5 divided by 1. So as that number in the denominator is getting bigger and bigger and bigger, you're getting closer and closer to 0. So let's take a look at these two examples, and then we can finish up here. So the limit as x approaches 0 of the quantity -3 plus 1 over x to the 4th. So this looks like it's a sum and difference, and then also one of those quotient properties. So the limit so basically we could think of this as the limit as x approaches 0 of -3 plus the limit as x approaches 0 of 1 over x to the 4th. Okay, so the limit as x approaches 0 of a constant, finding the limit of a constant is just that constant, so it's going to be -3. And if I'm finding the limit as x approaches 0 of 1 over x to the 4th, we have to kind of think about what's happening as I approach 0 from either side. So if I pick some really small number like 0.1, and I raise that to the 4th power, that means that my denominator is getting very, 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 very small. So with a small denominator, that means that overall your number is getting bigger. If I plugged in something like -0.1, -0.1 to the 4th is also getting very, 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 very large because you're raising it to the even power, so it's going off to a positive infinity. So both sides go to positive infinity around x equaling 0. So this is -3 plus infinity. And remember, when you add or subtract some number from infinity, then you just get infinity as your limit. So that means the limit as x approaches 0 of -3 plus 1 over x to the 4th would be infinity. Let's take a look at part B. Part B says the limit as x approaches 0 from the right, so we're just looking at a right-handed limit, of x plus 4 over the opposite of the natural log of x. So this is a quotient. So if I'm looking at the numerator is continuous everywhere. The denominator has some restrictions in our domain, but let's think about what's happening here. Okay, so in the numerator, if we're taking the limit of the numerator, the limit as x approaches 0 from the right of x plus 4, that's going to be just 0 plus 4, which is going to be 4. And then I can divide that by the limit as x approaches 0 from the right of the opposite of the natural log of x. And then I can actually pull this negative out because it's a scalar multiple, and I can just consider what's happening to the natural log. So 0 from the right in this is just going to be 0 plus 4, since this is continuous everywhere. Then that means that this limit is going to be just 4. And then in the denominator, thinking about the natural log function. So the natural log function is the inverse of a exponential function, and it's only defined for x values that are greater than 0. So at 0 it does not exist, but as I'm approaching 0 from the right in my natural log function, it looks something like this. It has a vertical asymptote here at 0. So as I'm approaching 0 from the right in the natural log function, this is going off to negative infinity. But then we're multiplying it by a negative, so that's going to go off to positive infinity. So it's going to be 4 divided by positive infinity. And remember, when I divide by something that is getting increasingly large, then that means my whole quotient ends up going to 0. So the limit here is going to be 0. These next two examples we will go through together in class. So go ahead and finish up here, and we'll go over parts C and D together in class.